Here we're going to look at a really interesting infinite sum that's got all of your favorite numbers involved. So we've got the golden ratio phi, we've got Fibonacci numbers, we also have the square root of 5, and our solution, or the value that we'll find for this sum, also involves probably one of your favorite constants. So let's see what we've got. Our goal is to find the square root of 5 times the sum as n goes from 0 to infinity of minus 1 to the n times f sub 2n plus 1 over 2n plus 1 times phi of 4n plus 2, where, like I said before, f sub n is the nth Fibonacci number, phi is the golden ratio. In other words, it's the positive root of the quadratic equation x squared equals x plus 1. And maybe along the way, we're going to need a couple of tools just to streamline this process. The first is this generating function for the odd terms in the Fibonacci sequence, but it's like kind of a weird generating function. Notice it has, well, the odd terms in the Fibonacci sequence, but then also it's got a power of 2n attached to the x. But that's okay, we'll get to that. And then there's this other relation down here with the golden ratio and the square root of 5 that we'll also derive. And then once we've got these two things at the ready, we'll work through the final calculation. Okay, so let's start with this one right here, this first thing. Okay, so let's introduce a little bit of notation. I'm going to take f of x and I'll set it equal to the sum as n goes from 0 to infinity of fn plus 1 times x to the n. So that means I've got something like this. I've got f sub 1 plus f sub 2x plus f sub 3x squared, and so on and so forth. So of course, since we probably are familiar with the starting Fibonacci numbers, it goes something like this. We'll have 1 plus x plus 2x squared plus 3x cubed plus 5x to the 4 plus 8x to the 5, and then it's going to go on and on and on and on and on. So this is slightly different than maybe the standard generating function for the Fibonacci sequence, but that's okay. We'll work with this here. So our goal is to get a closed form for this sequence. And we're going to do it the classic way by pulling out the first two terms and then maybe using the recursion. Okay, so let's do that. So we can write this as 1 plus x. So that's pulling out the first two terms. Actually, I think here I only really need to plug out the first term. So I'll have 1 plus, and then I'll have the sum starting at n equals 1 to infinity of fn plus 1 x to the n. And now I'm going to use the Fibonacci recursion on this fn plus 1 term. And that's probably well known. That'll give us f sub n plus fn minus 1. And then I'll split those into two sums. So that'll give me something like 1 plus, now I'll have the sum as n goes from 1 up to infinity of f sub n x to the n. And then next I'll have the sum as n goes from 1 to infinity of fn minus 1 x to the n. So something like that. But now I'd really like to re-index this so it looks like my original series up there. So how can I do that? Well, in this first bit, I can take all of the n's and replace them with n plus 1. And then in this second bit, I can take all of the n's and I'll replace them with n plus 2. That'll make everything work out. So let's see what that leaves us with. So we'll have 1 plus, now we'll have the sum as n goes from 0 to infinity of fn plus 1 times x to the n plus 1. So why is this at 0? Well, notice if we exchange n for n plus 1, when n plus 1 is 1, n is equal to 0. But now I want this to look exactly like our starting series. So I can do that by taking this x to the n plus 1 and factoring an x out by putting it right here. So that'll be a little bit better to work with. Now let's see what we have for this next bit. So now we'll have the sum as n goes from 0 to infinity. You might say, well, shouldn't we go from -1 to infinity? And in fact, we don't really need to do that because we'll take those lower terms to be 0. Now we'll have fn plus 1 again times x to the n plus 2. But I'll take that plus 2 and bring it out here as an x squared. Oh, but check it out. We have re-achieved our starting sum 2 different times. So notice both of these things that I'm overlining in peach are exactly our f of x. So that gives us a nice functional equation. So we've got f of x equals 1 plus x times f of x plus x squared times f of x. So putting that all together, we have f of x equals, well, what will it be? It'll be 1 over 1 minus x squared. So that's what we've got there. Okay, so now let's bring that up. So this is where we just ended. So we've got the sum as n goes from 0 to infinity of the n plus first Fibonacci number times x to the n equals 1 over 1 minus x squared. Now from here, I'm going to take all of the x's and replace them with negative x. So let's say that's what this yellow arrow means. So I'm going to take x and I'll replace it with negative x. So what'll that deposit us? So now we'll have the sum as n goes from 0 to infinity. We'll have minus 1 to the n times fn plus 1 times x to the n. So that's what we get on the left-hand side. I broke that negative x all to the n power into 2 parts. And then on the right-hand side, we'll have 1 over 1 plus x minus x squared, just because we've got even and odd exponents right there. So now what we'll do is take these two expressions and add them. So where does that leave us? So now we'll have the sum as n goes from 0 up to infinity of 1 plus minus 1 to the n times fn plus 1 times x to the n equals 1 over 1 minus x squared plus 1 over 1 plus x minus x squared. But now you can probably see that we're getting very, very close to this first little goal that we had. And let's note that this is maybe a choice function of, or maybe a question function of, are you even or are you odd? So is n even or is n odd? So in fact, what we get here is this collapses to 0 if n is odd, but this collapses to 2 if n is even. It's just a matter of that canceling each other out or doubling up. Okay, so if n is even, then we can replace n over here with 2n, and we'll be left with 2 times the sum as n goes from 0 up to infinity of f sub 2n plus 1 times x to the 2n. But then we don't really need to look at what's happening when n is odd because we get cancellation there. So that fills in this gap. So we really have 2 times this series is equal to the sum of these two rational functions. But if we divide both sides by 2, we get exactly this expression. Okay, so next up we're going to look at this nice little identity involving the golden ratio and the square root of 5. And you might say, well, this is super simple. I could just derive this from the closed form of the golden ratio, and for sure you could. But instead of doing it that way, I'm going to derive it from the fact that the golden ratio is a root of this polynomial equation right here. I think that's a little bit more interesting. So we'll essentially start with the left-hand side and see where we go. So here we've got phi to the 4 minus 1 over phi squared. And let's maybe put a little bit of a box right here just to point out that we know that phi is positive and also that phi squares to phi plus 1. That's because the golden ratio is the positive root of that polynomial equation. Okay, so now let's factor out the numerator. So that's going to factor as phi minus 1 times phi plus 1 times phi squared plus 1. I don't think much needs to be said about that. That's just a simple factorization of the difference of squares a couple of times. But check it out. This phi plus 1 will cancel with this phi plus 1. And then we can replace this phi squared with a phi plus 1. So that's going to leave us with phi minus 1 times, well, let's see, that'll be phi plus 2, because we'll have phi plus 1 plus 1. Now let's multiply that out. So we'll have phi squared, and then plus phi minus 2. But then again, making this replacement, what will we be left with? Well, we'll have 2 times phi minus 1. So that's what happens after a little simplification. But I'm telling you that should be the square root of 5. Well, first of all, we know that this is positive. And I guess here I'm thinking that's because I know the closed form of phi, but I bet you could prove it from this defining relation over here. We won't really worry about that. But how would we show that it's the square root of 5? Well, we're going to simply square it and show that we get 5. So let's do that. So let's take 2 phi minus 1 squared. That squares to 4 phi squared minus 4 times phi plus 1. But now this is going to be 4 times phi plus 1 minus 4 phi plus 1. Again, using this. Oh, but check it out. All of the phi's cancel and we get 5. So the fact that that squares to 5 and the fact that this is positive tells us that in fact 2 phi minus 1 is equal to the square root of 5. But following this equality up here, we see that phi to the 4th minus 1 over phi squared is the square root of 5, but that's exactly our second tool. Okay, now we're ready for our main goal. And the trick will be to express this kind of main goal sum as an integral of, well, this power series. Well, it's not exactly just an integral. What it'll be is an integral times a constant. Okay, so bear with me here. We're going to write something that looks a little bit crazy to start with. So I'm going to write that this is equal to negative I times the square root of 5. And then the sum, as n goes from 0 to infinity, of f sub 2n plus 1 over 2n plus 1 times, let's write this as I over phi squared raised to the 2n plus 1. Okay, so notice if we raise I to the 2n, we get negative 1 to the n. But then we've got an extra I to the 1, but that's going to cancel with this minus I out front. So that's how all of this works. But looking at it like that, it really looks like an integral. Notice we've got an exponent here, which is 2n plus 1, and that thing is in the denominator. That 2n plus 1 is in the denominator. It looks like we've integrated and evaluated. And in fact, that's exactly how we'll write this. So this will be minus I times the square root of 5 times the sum as n goes from 0 to infinity, and then we'll have the integral from 0 up to I over phi squared of f sub 2n plus 1 times x to the 2n. Okay, so let's look at this again. Notice if we raise the exponent by 1, divide by the new exponent, and evaluate it at I over phi squared, we get exactly what we have up there. So everything looks good. But now I'm going to exchange the order of summation and integration. That's allowed here. That'll give me minus I times the square root of 5. Then we'll have the integral from 0 up to I over phi squared of, now we've got our sum as n goes from 0 up to infinity of f 2n plus 1 times x to the 2n dx. Okay, great. But that integrand right there is exactly what we just spent a bunch of time getting a closed form of in terms of this generating function. So let's make that replacement. So here we have this is minus I times the square root of 5. And then we have our integral from 0 up to I over phi squared of, well, I've got a 1/2 times the sum of those two. So I'll maybe bring my 1/2 out. So I've got that half out there. And then I'll have 1 over 1 minus x squared plus 1 over 1 plus x minus x squared dx. Great. So that's where we are at the moment. Okay, so now from here, we're going to complete the square of those two terms in the denominator. So let's maybe complete the square of their negatives because that's just a little bit easier to work with. So if we've got x squared plus x minus 1, so that's the negative version of this one, well, we can rewrite that as x squared plus x plus quarter and then minus 5/4. Or in other words, x plus 1/2 quantity squared minus 5/4. So something like that. So that means that we can take this first term and replace it with 1 over 5/4 minus x plus 1/2 squared. And then via a very, very similar calculation, we can take this second term and replace it with, let's see what it'll be. It'll be 1 over 5/4 minus x minus 1/2 squared. So, like it's kind of similar there. And then next up, we're going to multiply by 2 over 2. We're going to multiply by 2 over 2 to build this 2 in the denominator up to a 4. And then we can distribute it through to here to cancel both of those denominators. So that's going to leave us something like this. So we still have our minus I times root 5 out front, our integral from 0 to I over phi squared, and now we'll have 2 over 5 minus 2x plus 1 squared plus 2 over 5 minus 2x minus 1 squared dx. Okay, great. So again, like we built that 2 up to a 4, that's going to cancel this 4 in the denominator, but when it enters the square, we've got to take the square root, but that's going to cancel that down. Okay, so let's start there. Okay, so this is where we just landed, but now we're going to do a partial fraction decomposition on both of these rational functions. That's essentially why we completed the square there. So I'm going to recall this kind of standard difference of squares partial fraction decomposition rule over there, where we've got a as maybe an arbitrary number. Here a is obviously equal to the square root of 5. So notice I get this 1 over a, which in our case is a 1 over the square root of 5. But that's going to cancel the square root of 5 right here. Furthermore, I forgot that I needed a 2 here, but I've got a 2 in both of those cases. So we're good to go. Okay, so that's going to leave me with the following object. So I'll have I think that should have been a minus I. And then I'll have the integral from 0 to I over phi squared. And then we'll have 1 over 2x plus 1 plus the square root of 5 plus 1 over 2x minus 1 plus root 5, and then minus 1 over 2x plus 1 minus root 5, and then minus 1 over 2x minus 1 minus root 5. So I reordered everything to put the pluses and the minuses together, but I kind of think that's okay. But now where can we go from here? Well, from here what we'll do is, well, we've got standard antiderivatives here. They'll be logarithms. So we'll have the log of this denominator. Well, that's actually going to be times 1/2 because we have this 2 as a multiplier of x. And I'm going to group the 2 pluses together and the 2 minuses together using logarithm rules. So that's going to leave me with minus I. And then actually I'll write that as minus I over 2 because I get a half for all of those antiderivatives. And then I'll have the natural log. I'm going to actually write that as log because we're about to work with complex numbers of 2x plus 1 plus root 5 times 2x minus 1 plus root 5. That's from the attachment with a plus. And then minus log of 2x plus 1 minus root 5, and then 2x minus 1 minus root 5. And then we're going to evaluate that from 0 up to I over phi squared. Okay, so that's looking good. But next up, I'm going to push these two linear terms together. So I'll multiply those two together, and I'll also multiply these two together. So I won't go through all of the details, but we end up with something that looks like this. So I'm just bringing down everything that we need. So we'll have a 4x squared, and then a plus 4 times root 5x, and then plus 4. And then we're gonna have something similar over here, so it'll be the log of 4x squared minus 4 root 5x plus 4. Okay, nice. But now we can split each of these into two parts. We can split these into the log of 4 plus the log of, in this case, x squared plus root 5x plus 1. And then over here, we'll have a minus log of 4 and then a minus log of, well, the same kind of thing, x squared minus root 5x plus 1. And then, of course, we have that evaluation as well, but we'll maybe hold on to that for the next calculation. So notice these log 4s cancel. Okay, we still have this minus I over 2 and this evaluation from 0 to I over phi squared, but we'll wrap that up on the next board. Okay, so this is where we just were. I took my evaluation and I wrote it as a limit, but that's essentially the same thing. Now we're about to have some complex logarithms, so let's just recall how that goes. So the log of a complex number written in polar form, i.e. r times e to the I theta, is equal to the natural log of the modulus of r plus I times theta. And then if we've got it in rectangular form, it's a little bit more complicated, but not much. We have the log of a plus bi is equal to the natural log of a squared plus b squared plus I times, well, the argument. The argument is the angle and the plane that this makes, but for these numbers, we get the arctan of b over a. So let's see how this goes. So I'm gonna take this and I'm gonna make a replacement of x with ix. So that's gonna change this limit into, well, now we've got minus I over 2, and then the limit as x approaches just 1 over phi squared, and then I'll have the logarithm of, well, let's see, this is gonna be 1 minus x squared, and then plus I times root 5x. So again, that's from the replacement of x with I times x, using the fact that I squares to -1. And then we're gonna have something similar over here. So we'll have minus the logarithm of another 1 minus x squared. And now it'll be minus I times the square root of 5 times x. Great. And now we can use this rule down here. So this is going to be minus I over 2. We have this limit as x approaches 1 over phi squared. And then now we're going to have the natural log of, well, it'll be a squared plus b squared, but that's going to be, in this case, 1 minus x squared squared plus, that'll be 5x squared. Okay, great. And then we'll have plus I times the arctan of the quotient of the imaginary part with the real part. That's what's going on right here. So this will be root 5x over 1 minus x squared. But now let's line that up with what we get with this other bit. So we'll have minus the natural log of another 1 minus x squared squared plus 5x squared, because check it out, those have the same modulus. And now we'll have minus I times the arctan of, this is going to be minus root 5x over 1 minus x squared for similar reasons. But now we get some cancellation and some doubling up. So notice this term will cancel this term because they're equal but have opposite signs. And then we can use the fact that the inverse tangent, the arctan, is an odd function. That changes this from a minus to a plus, and that from a minus to a plus. Next up, those two are going to build up to 2 times arctan. That's going to cancel this 2 in the denominator. We've got an I multiplying by the negative I will simply leave us with 1 because I times negative I is 1. And we are finally left with the limit as x goes to 1 over phi squared of arctan of the square root of 5 times x over 1 minus x squared. But now I'm going to take this argument of the inverse tangent and multiply the numerator and the denominator with 1 over x squared. So that's going to change this to 1 over x there because we'll have x over x squared. And then this will be 1 over x squared minus 1. So now pushing this limit inside, we'll have the arctan of the square root of 5 times, this will be phi squared over phi to the 4th power minus 1. Oh, but check it out. Phi to the 4th minus 1 over phi squared is the square root of 5, but if we take the reciprocal, we have 1 over the square root of 5, but that's going to cancel this square root of 5 in the end, leaving us with arctan of 1, which is pi over 4. So there we have it. We have finished our sum and we've gotten to another probably of your favorite constants, pi. And that's a good place to stop. Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.